So this problem is interesting in that we have a spring that doesn't conform to Hooke's law. Sometimes that's called a non-Hookean spring. And in part A, we have to compute the work done. Well, this is a situation where the work is being done by a variable force that as x changes, F will change. So the only way to do that is through integration. That's what the formula looks like. So we are going to have to integrate, and they want us to do this from 0.5 to 1 meter. So from 0.5 to 1 meter, we're going to integrate that function, which is 52.8x plus 38.4x squared. So that might look intimidating, but you just follow the basic rules of integration, which are to raise the exponent to the next higher power. So this x becomes x squared. Divide by that new power, so I'm going to divide that by 2. And then for the second situation, raise to the next higher power, which is x to the third, and then divide by that new power. And technically that's plus c, but we're going to evaluate that from 0.5 to 1. So let's do that. So let's put 1 into that equation. 52.8 divided by 2 is 26.4. Times 1 squared plus 38.4 divided by 3 is 12.8 times 1 cubed plus c minus what you get when you put in 0.5 to those locations. And the result, if you do all that math, this part is 39.2. This part is 8.2. Of course, that's plus c here, plus c there. But the c's will cancel out. And you end up with 31 joules. So that is the answer to A, 31 joules. All right, what do they ask us to find in part B? They're attaching a mass when it's stretched to 1 meter, and then they're letting it go. And we're trying to figure out what its speed will be when it's at 0.5 meters. Well, this sounds like an uck-wuck problem. So U at A plus K at A plus W and C equals U at B plus K at B. So at point A, now here, in reality, springs are conservative forces. And you could put into A the potential energy that the spring has at A and the potential energy that the spring has at B. But maybe you don't know that. Maybe you don't know that this is a conservative force. So, well, even if it is a conservative force, you could look at it as a non-conservative force. And so let's do it that way. So I'm going to say the potential energy at A is 0. The kinetic energy at A is 0. This is where it's attached to the spring that is stretched 1 meter. And now we have to figure out how much work does the spring do as it goes from being 1 meter stretched to 0.5 meters stretched. Well, that's the number we just calculated. It does 31 joules of work. And if you have some question about the positive or negative sign there, think of it this way. The spring pulls on the mass, and the mass moves in the same direction that the spring is pulling. So it is a positive 31. On the other side of the equation, again, we're not assuming that this spring creates potential energy. And the kinetic energy of the mass is what we're interested in. So it's 1/2 2.17 times the speed at B squared. And if you solve for speed at B, you get 5.35 meters per second. 5.35 meters per second is the answer that you get there. Now the last part of that question asks you to say whether or not the spring's force is a conservative force or not. And I think the best way to answer that is that one of the official tests of a conservative force is if the work done by it only depends on the initial and final position and not on the pathway itself. And that is the case when you look at this equation. The equation up here for force has position. X stands for position, not length of a pathway. It stands for position. And so when we calculate work, all that matters is what's the final position and what's the initial position. And there's nothing about this equation that takes into account the pathway for those two different positions. So that means this is a conservative force.